Have you ever opened up a massive production drawing, just completely covered in complex dimensions, datums, position tolerances, and profile controls, and felt, well, entirely overwhelmed? If you have, you know exactly what I'm talking about. Today, we are diving deep into the complete geometric dimensioning and tolerancing, or GD&T workflow. We're breaking down advanced drawing interpretation based on our source material so you can actually read these prints like a seasoned engineering pro. Welcome to this explainer, where we're going to synthesize all these advanced concepts together. Let's get right into it.
So, here is our roadmap for the lesson. We'll be looking at the complete workflow, a systematic drawing review process, real-world interpretation, manufacturing strategy, some super common mistakes, and then we'll wrap it up with our key takeaways.
But before we go any further, I really want to start by asking you this crucial question. Do you just know the symbols, or can you actually read the drawing? Because let's be honest, memorizing that a perpendicularity symbol looks like an upside-down T is vastly different from understanding how an entire part actually goes together out there on a manufacturing floor. Real-world engineering requires you to understand the living, breathing relationship between your dimensions, your datums, and your geometric controls all at the exact same time.
Okay, Section 1, the complete GD&T workflow.
I saw this observation from an experienced mechanical engineer on an engineering forum, and it just perfectly hits the nail on the head regarding the disconnect we see in the industry. They mentioned that there's a serious fly-by-the-seat-of-your-pants mentality happening out there. Designers sometimes forget their audience. GD&T extends way beyond just making a drawing that looks good for your boss. It's a universal design language. It's a communication tool spanning design, manufacturing, and inspection. When you just wing it, you end up with prints that have way too much detail where nobody needs it, and a total lack of detail where it's absolutely critical.
The thing you have to remember is that every single department uses the exact same drawing. It's the single source of truth. The designer uses it to set those ideal functional limits to make sure the part works. But then, manufacturing gets that same piece of paper, or file, and they have to interpret those exact same tolerances to figure out their machining setup, their fixture planning, and their tooling. Then quality and inspection step in, they use it to confirm the standards are met. And finally, assembly relies on it to ensure physical fit. So what does this mean? It means the language of GD&T has to explicitly guide how design intent flows straight into physical production. If there is any ambiguity, the whole system just breaks down.
Let's move on to Section 2, the systematic drawing review process.
To stop that fly-by-the-seat-of-your-pants approach, you need a repeatable workflow. By following these 6 chronological steps every single time you open a print, you completely eliminate ambiguity. Step 1, always review the title block. Don't just gloss over it. You cannot rely on default title block tolerances for critical features, but you absolutely must know what they are as your baseline. Step 2, read the notes. They almost always contain crucial manufacturing or process constraints. Step 3, identify your critical to quality features. Step 4, locate the datums. Step 5, break down the feature control frames applied to those specific features. And finally, Step 6, take a step back and understand the functional relationships. How are these features going to interact during final assembly? Doing this in order guarantees you never miss the underlying design intent.
All right, Section 3, Real-World Drawing Interpretation.
You know, you really have to contrast the ideal world of your 3D CAD model against the gritty reality of mechanical variation. Think about it. In your CAD software, planes are mathematically flat. Axes are these perfect imaginary lines floating in space. But manufacturing? They have to deal with physical realities. They're dealing with tooling marks, machine chatter, real-world fixturing constraints, and varying material conditions. As an engineer, you have to constantly remind yourself that a machinist cannot fixture a block of steel on an imaginary center line. They have to grab real, physical surfaces.
Interpreting these drawings also means you've got to stay current with the standards. For instance, look at the ASME Y14.5 2018 update. Did you know they completely removed the symbols for concentricity and symmetry? Yep, they were too easily misunderstood. So now they're replaced entirely by position or profile controls. They also updated the terminology from true geometric counterpart to datum feature simulator. Honestly, that's a brilliant change because it clearly separates a perfect theoretical cylinder from the actual physical chuck or collet they use on the shop floor. Plus, they added Rule 4.1Q to explicitly clarify that basic as-designed dimensions do not establish a manufacturing target on their own.
This visual here is a fantastic example of the 2018 revision in action. Notice how the center of the radius is specifically located by those basic dimensions, the crosshairs at 14 and 28. Under the updated standard, this means the resulting boundary arcs are concentric. That one little detail completely changes how the profile tolerance zone is interpreted and ultimately measured compared to an unlocated radius. If you're not aware of this update, you are definitely going to inspect this part incorrectly. Moving right along to Section 4, Manufacturing and Inspection Strategy.
Let's think about physical inspection for a second. The datums you choose when you make that drawing directly dictate how this inspector or a CMM programmer is going to set up their coordinate system. It is incredibly easy to just pick whatever you want to measure from a mathematically perfect CAD model, but if the physical datums you've selected aren't actually consistently measurable on the real part, maybe the surface is way too small or it's inherently unstable, that's going to cause propagated measurement errors. The result, perfectly good, functional parts are going to look like scrap on the inspection report.
And this is exactly why modern workflows are leaning so heavily into intelligent model-based GD&T, or MBD for short. Instead of relying purely on 2D prints where, let's face it, a programmer might easily misinterpret a complex datum precedence, MBD uses semantic 3D CAD data. Software can just pull in this native data, automatically recognize really tricky things like composite positions or simultaneous requirements, and instantly build an inspection plan. It literally bounces the QC data right against the 3D authority in real time. This is a total game changer because it eliminates manual data entry and those incredibly costly human interpretation errors.
All right, let's talk about where things go wrong. Section 5, Common GD&T Mistakes.
Even with the absolute best tools in the world, human error is always a factor. These are the top mistakes we see that just balloon production costs and cause massive assembly nightmares. First up, over-tolerancing. Designers love to play it safe by slapping tight tolerances on non-functional features, which instantly spikes manufacturing costs. Then there's completely mixing up material condition modifiers. Remember, maximum material condition, MMC, is typically for clearance fits. Least material condition, LMC, is often to protect minimum wall thickness. If you swap those around, you're asking for functional failures. Finally, ignoring downstream tolerance stack-ups or forgetting to update the GD&T when you tweak your CAD model, those are surefire ways to get a whole batch of rejected parts.
I really want to hammer this point home again. Please do not pick datum features just because their individual dimensions happen to be super tight, or because they represent a really convenient imaginary axis in SolidWorks or whatever you use. That's not what datums are for. Datums exist so the physical part can be reliably fixtured, stabilized, and measured in a reasonable coordinate system. If you select non-functional surfaces, you will instantly compromise how that part fits and functions in the final assembly. And believe me, the assembly team will definitely let you know about it.
Which brings us to Section 6, Key Takeaways and Capstone.
So what's the big picture here? The crucial takeaway is that mastering GD&T means you have to think way beyond your own desk. It is the ultimate bridge between your design intent and cold hard manufacturing reality. So whenever you open a drawing, force yourself to use that 6-step review process. Stay sharp on those ASME Y14.5 2018 updates. And always ask yourself 3 things. Is this tolerance feasible to actually machine? Is it realistically measurable by the quality team? And is it truly functionally necessary for the final assembly?
You now have the professional framework to confidently interpret complex production prints. The source material finishes up by setting the stage for a capstone project, a final drawing analysis to put all this together. But before you tackle your next real-world print, leave yourself with this thought. Is your GD&T workflow actually building a reliable bridge to manufacturing reality? Or are you just sketching imaginary perfection on a private island? Thanks for joining me for this explainer. I'll see you in the next one.